Hello students, welcome back to the lecture series of fluid mechanics. We are discussing on unit number 1 basics of fluid mechanics. This is lecture number 15 and almost here we are going to complete the chapter number 1. Today we are going to see the numericals on pressure measuring devices. In last lecture we have discussed about classification of fluid mechanics or classification of pressure measuring devices. So in that we have discussed about manometers and mechanical gauges are the two different devices used for the measurement of pressure. The manometers having certain limitation that it can be used to measure the pressure of very limited small range, whereas mechanical gauges having a diverse range for the measurement of pressure. Again, manometers gives more accurate results in terms of height variation of fluid, whereas in mechanical gauges also we are getting a good quality of results. Manometers again classified into two categories, simple manometers and differential manometers, whereas mechanical gauges are classified into four categories: diaphragm type, Bernoulli's tube type, dead gauge pressure type, and bellow pressure type of pressure gauges. So all those mechanical pressure gauges are dependent on the elasticity of material which is used for the measurement of pressure, where in a diaphragm type of pressure gauge, diaphragm type of arrangement is provided where the displacement is taken place due to the increase in pressure of a diaphragm. In a Bernoulli's tube type of pressure gauge, G-shaped elliptical cross-sectional tube is used where the tube tries to be straightened due to the applied pressure. In deadweight pressure gauge, a standard calibrated pressure weights are used for comparison of pressure, and in a bellow pressure type of pressure gauge, bellow is used for the measurement of pressure where it gets expanded due to the application of pressure. So these are the some different kinds of pressure gauges used for the measurement of pressure. Depending on that, we are going to solve some numericals. So in a simple manometer, we will see first a piezometer, which is used for the measurement of pressure. So piezometer is nothing but a device. It is a simple tube, vertical tube connected to the device whose pressure we wanted to measure, and with the help of height difference it can be possible to measure the fluid pressure. Now consider a point A where we want to measure the pressure. The tube is connected at the level of A, and H is nothing but the rise of fluid pressure level inside the tube. So here with the help of piezometer, pressure can be given as P is equals to rho into G into H. So by using this formula we are going to solve some numericals. Now consider this is the first numerical. The pressure intensity at a point in a fluid is given in 5 Newton per centimeter square. Find the corresponding height of fluid when fluid is first water, second is oil with specific gravity of 0.80, and third is the kerosene of specific gravity of 0.74. What is the specific gravity of water? Specific gravity of water is 1. Why it is 1? Because specific gravity is calculated with the density of fluid to the density of standard fluid, and here the standard fluid we are going to consider as a water, and that's why specific gravity of water is equals to 1. Now from given data, pressure is given, it is 5 Newton per centimeter square. If you want to convert it in a meter, multiplied by 10 to the power 4 Newton. Here by mistake I have put out centimeter square. So pressure is nothing but pressure is 5 into 10 to the power 4 Newton per meter square. 4 Newton per meter square. Now we wanted to calculate the height H. So we know that for water P is equals to rho into G into H. So H can be given as P by rho G, P divided by rho G. So for water purpose it is 5 into 10 to the power 4 divided by density of water is 1000 into G is nothing but gravitational acceleration is 9.81. So by this formula H can be given as 5.096 meter. Similarly for oil purpose, since specific gravity is 0.80, so its density of fluid, specific gravity is nothing but density of fluid divided by density of water. So therefore density of fluid is nothing but specific gravity into density of water. So here rho can be given as 800. So for oil purpose again P is equals to rho GH. So H can be given as P by rho G. So it is nothing but 5 into 10 to the power 4 divided by 800 into 9.81. So height, level of rise of water, H can be given as it comes nearly about again 5.09 meter. And third is one is the kerosene. Again for kerosene, P is equals to rho into G into H. Here again H can be given as rho by GH, P by rho G. So rho can be calculated as rho is equals to specific gravity into density of water. So 0.74 into 1000, it is nothing but 740. So H can be given as 5 into 10 to the power 4 divided by 740 into 9.81. So here again H should be calculated. I'm not sure that this H value is by mistake I have put out same 5.96, but by calculation you check what values are coming. Okay, so by this you will be able to calculate the rise in water level or fluid level. Now we'll go for the U-tube manometer. Again, it is a simple type of manometer. So in regarding U-tube manometer, we know that in a manometer we are placing the fluid just like a mercury, and due to the increased pressure inside the container, that mercury level is shifted from its datum from position H1 to H2, and here the change in height is considered as H1. So we know that pressure above AA line at right column is equals to rho 1 GH1, and pressure above AA line at left column is nothing but P plus rho 1 into GH1. So equating two pressures, we can calculate that pressure at point B is equals to rho 2 GH2 minus rho 1 GH1. So by that formula here it can be possible to measure the pressure. Okay. Now consider this as a problem. A U-tube manometer contains the mercury as a monomeric liquid. One end of manometer is connected to a pipe in which a fluid of specific gravity is 0.8. The level of mercury in right limb is 8 cm above the center of pipe. Then calculate pressure of a fluid in a pipe with the difference of mercury level in two limbs 18 cm. Now this is the problem where pipe A is connected to U-tube manometer, with the help of which we wanted to measure the pressure inside the pipe A. So at a particular point A, to measure the pressure, U-tube manometer is connected. Now from datum point, its height is 18 cm, and the rise of mercury level from its position is nothing but 8 cm. Is 8 cm. Now we know that, and again they have given the specific gravity of 0.8. Specific gravity of 0.8 of the fluid. Now we know that for mercury purpose the specific gravity is 13.6. So we know that specific gravity is nothing but again a density of fluid divided by standard density of fluid. So it is nothing but of water, it is nothing but 1000. So density of fluid A can be given as 0.8 into 10 to the power 3 kg per meter cube, and density of mercury is nothing but 13.6 into 10 to the power 3 kg per meter cube. Have you understood how comes rho m is equals to 13.6 into 10 to the power 3? Because we know that standard density of mercury is 13.6. Specific gravity of mercury is 13.6. So density of mercury is nothing but specific gravity into density of water. So 13.6 into 1000 is nothing but 13.6 into 10 to the power 3 kg per meter square. It is the density of mercury. Now we wanted to calculate pressure at point A. So pressure at point A, height can be given as 18 cm, is nothing but 0.18 meter, and height at towards the A is nothing but height difference between that point is 8 cm, is nothing but 0.8 meter. So in equilibrium condition, so from figure pressure in left limb above xx is equals to pressure in right limb above xx. So here the pressure difference between point A to xx is nothing but h1, and pressure difference between x to top is nothing but h2. So h2 value is 18 centimeter. Now we have to calculate h1, because we know that PA plus rho A G H1 is equals to rho M G H2. Rho M G H2. So H1 can be calculated as 18 minus 8. That is nothing but 10 centimeter. We have to convert it into meter. So it is nothing but 0.1 meter. So PA from above equation we can write as PA plus rho A into G into the pressure difference, that is height difference H1 is equals to rho M G into height H2 0.18. So we can write this equation as PA is equals to rho M G into 0.18 minus rho A G into 0.1. Now rho M is nothing but 13.6 into 10 to power 3. G is nothing but 9.81 into H is nothing but 0.18 minus again rho A is nothing but 0.8 into 10 to power 3 into G 9.81 into H is nothing but H1 is nothing but height difference between H2 and above height, that is 18 minus 8 is nothing but 0.1 meter. So by this formula, PA can be given as PA is equals to 23,230.8 not 8 Newton per meter square. Okay, you also try to solve this problem by doing the calculations in your notebook. Now consider the second problem. The right limb of simple U-tube manometer containing mercury is open to the atmosphere, while the left limb is connected to the pipe in which fluid of specific gravity 0.9 is flowing. The center of pipe is 12 cm below the level of mercury in the right limb. Find the pressure of fluid in the pipe if the pressure level in the two limbs is 20 cm. So the difference of mercury level in the two limbs is 20 cm. Now here again in this problem, the difference between datum point to the height of right limb of your manometer is 20 cm, and difference between the level of fluid to the rise in height is 12 cm compared to the right limb. So here H2 is nothing but 20 cm, and H1 is again like that the previous problem is nothing but difference between total rise in water level mercury level at limb A minus rise in mercury level or difference in mercury level from that particular point. So H1 can be given as 20 minus 12 is nothing but 8 cm. Okay, so again like in the previous one, density of fluid can be calculated as rho 1 is equal to this 1 into 1000. So density of fluid is 900 kg per meter cube. Density of mercury is nothing but 13.6 into 1000 kg per meter cube. H2 is nothing but 0.2 meter. H1 is equals to 20 minus 12 is equals to 8 cm is equals to 0.08 meter. Now pressure of fluid in a pipe we consider as P. Now equating the pressure above A line can be given as PA plus rho A G H1 is equals to P2 G H2. So P can be calculated as P is equals to rho 2 G H2 minus rho 1 G H1, or here it should I have written as P plus 900 into 9.81 into 0.08 is equals to 13.6 into 1000 into 9.81 into 0.2. So P can be given as a difference between these two, and therefore P is equals to 25977 or 25,977 Newton per meter square. So this is nothing but the pressure inside the manometer tube. Okay. Now we're going to go for the second category consideration, that is for vacuum pressure purpose. Now suppose container B having the vacuum pressure, then due to the vacuum, mercury level in right limb will decreases instead of increasing due to the pressure, and mercury tries to shift towards the container. Let H2 be the total shift of mercury towards the container, and H1 be the difference in a pressure or a difference of fluid pressure inside the container, and B be the point where we wanted to measure the pressure. Then again, according to the equilibrium condition, ρ2 GH2 pressure above AA line in the left column is equals to ρ2 GH2 plus ρ1 GH1 plus PB, and at right column it is equals to 0. So equating this equation, ρ2 GH2 plus ρ1 GH1 plus PB is equals to 0, or PB is nothing but minus ρ2 GH2 plus ρ1 GH1, and here negative sign indicates the negative pressure, that is, it indicates vacuum pressure. Okay, now consider a problem. A simple U-tube manometer containing mercury is connected to the pipe in which a fluid of specific gravity 0.8 and having vacuum pressure is showing. The another end of manometer is open to the atmosphere. Find the vacuum pressure in a pipe if the difference of mercury level in two limb is 40 cm and height of fluid in the left of the center of pipe is 15 cm below. So this is the problem where the mercury level difference between left column and right column is 40 cm, but rise in mercury level is only in left column, and difference of fluid pressure or height is 15 cm. Now here again, in a problem, specific gravity is given. For fluid it is 0.8, so ρ1 is the density of fluid is nothing but 800 kg per meter cube, and ρ2 with the density of mercury is nothing but 13.6 into 10 to power 3 kg per meter cube for mercury. Okay, so we know that for vacuum pressure purpose, ρ2 GH2 plus ρ1 GH1 plus P is equals to 0. So putting the values at here, P can be given as P is equals to minus outside the bracket into 13.6 into 1000 into 9.81 into 0.4, that is ρ2 GH2 plus ρ1 is 800 G 9.81 into H1 is nothing but difference 0.15 meter. So the answer is minus 54543.6 Newton per meter square, or we can say minus 54.54 kilonewton per meter square. Okay, so this is about a simple manometer. Now we'll consider one problem with respect to the differential manometers. So suppose we wanted to measure the pressure difference between point A and point B and containing the fluid of a certain height, and as shown in this figure, then from equilibrium equation, P1 ρ1 G into H plus X plus PA is equals to rho G into H plus ρ2 G into Y plus PB. Now how this equation comes? See again carefully, look at the point. Fluid level at point, we wanted to measure the difference between pressure at point A and B. From A, the mercury level is decreases up to here, the cross sectional area or the bottom point XX. Now from A to XX, the total height is X plus H. Therefore, total pressure in left limb is equals to density of this fluid rho into G into this total height, and this total height is nothing but rho g into h plus x. Okay, so this is the rise of or fall of fluid level in the left column. It is due plus additionally pressure Pa, which is counterbalanced by right limb. Now in a right limb we have mercury as a fluid, so it is nothing but rho g is the mercury level up to the height h. So rho g into h plus this is the fluid 2 up to height y, therefore it is rho 2 g into y and plus pressure of Pb. Okay, so with this we wanted to solve the problem. If the fluid or liquid containers of pressure are at of same level, we wanted to measure the pressure at the same level, then the equation will be changes as rho g into h plus rho 1 into g into x plus Pb, that this side pressure, rho g into h plus rho 1 into g into x plus Pb is equals to rho 1 into g into h plus x, total height, h plus x plus P. Okay, a differential manometer is connected at 2 points A and B as shown in figure. At B, air pressure is 9.81 Newton per centimeter square. Find the absolute pressure at point A. Find the absolute pressure at point A. Now see this problem. A consists an oil of specific gravity 0.9. B consists an water, but in that container again it consists air above half level and it is of with air. So what is the effect of air at here? Since at it is atmospheric pressure, there is no any, I think there is no any pressure difference will be occurs. So at point B, the pressure is 9.81 Newton per centimeter square. So pressure at point B is nothing but 9.81 into 10 to the power 4 Newton per meter. Now density of oil is 900 kg per meter cube. Density of mercury is 13.6 into 10 to the power 3 kg per meter cube. Here now total height of fall of mercury is nothing but 600 centimeter. So H1 is equals to 0.6 meter. H2 is nothing but 0.2 meter. And H3 is again a 0.2 meter because total difference is given is 0.2 meter. So pressure at A is Pa. Taking datum line as an XX, we can write as rho 1 g H1 plus Pb is equals to 1000 into 9.81 into 0.6 plus Pb. So nothing but 5886 plus 98100, which is nothing but 1,03,986 Newton per meter square. Now above pressure line XX in a left limb, Pa plus rho A G H2. Now here rho H2 is shown as mercury, so I can say that here by mistake I have put out 10, it is equals to 20. So rho here it is mercury into density of mercury into G into H2 plus density of fluid inside this container into G into H. So it is nothing but 13.6 into 1000 into 9.81 into 0.1 about mercury, plus 900 into 9.81 into 0.2 plus Pa. So Pa can be given as 88,876.8 Newton per meter square. Okay. A U-tube differential manometer containing two pipes at A and B. The pipe A contains a liquid of specific gravity 1.5 under pressure of 100 kilonewton per meter square, and pipe B consists an oil with specific gravity 0.8 and with a pressure of 175 kilonewton per meter square. The pipe A is 3 meter above the pipe B. The height of liquid in the left limb is 4 meter below point A. Then calculate the difference in mercury level in the differential manometer. Okay. Now here A and B are the two pipes. A pipe is above 4 meter. So there is the height difference between the reservoir A and B. Now we have to calculate the difference in mercury level in differential manometer. So density of fluid A is nothing but 1.5 into 10 to the power 3 kg per meter square. Rho m with the density of mercury, it is nothing but standard 13.6 into 10 to the power 3 kg per meter cube. And rho of B is nothing but density of fluid B is nothing but rho B is equals to 0.8 into 10 to the power 3 kg per meter cube. Now especially height difference H is nothing but 0.4 meter. And we have to calculate the H. And the difference between pipe A and B is nothing but 3 meter. PB is given as 175 kilonewton per meter square. It is nothing but 175 into 10 to the power 3 Newton per meter square. So in equilibrium condition from figure, pressure in left limb is equals to pressure in right limb. Now here HB be the total fall in water level, fluid level from the bottom line XX. So at left hand limb, PA be the pressure inside the pipe A plus rho A GHA be the height of fluid level in left limb plus rho m into G into H, where H is nothing but height of mercury. Okay, is compensated by PB plus rho B G HB. Rho B is nothing but density of fluid B, G is the specific gravity, and HB with this height. HB with this height. Okay, so how to calculate then HB from figure? HB can be given as 4 plus H minus 3. 4 plus H minus 3. So it can be written as H plus 1. It can be written as H plus 1. So using above data, H can be given as 0.19 meter. Now for this purpose, you solve this problem by yourself. PA is given 1.5 into 10 to the power 3. Rho A is given, PA is given, PA is nothing but pressure at point A. So it is equals to 100 kilonewton per meter square. So it is nothing but 100 into 10 to the power 3 Newton per meter square. Rho A is given 1.5 into 10 to the power 3. G is nothing but 9.81. HA is nothing but 4 meter. Plus rho M is 13.6 into 10 to the power 3. G 9.81 into H is equals to PB. PB is given 1.75 into 10 to the power 3 Newton per meter square. Rho B is nothing but 0.8 into 10 to the power 3. G is nothing but 9.81. And HB here we have calculated as H plus 1. Now solve this equation. Here the two entities with only one unknown H, and solve this equation. You will get H value is equals to 0.191 meter or 19 centimeter. Well, this is the last problem. A differential manometer is connected to two points A and B of two pipes as shown in figure. The pipe A contains a fluid of specific gravity 1.5, while pipe B contains a fluid of specific gravity 0.9. The pressure at A and B are 1 kgf per centimeter square and 1.80 kgf per centimeter square respectively. Find the difference in mercury level in differential manometer. It is again a similar kind of problem with the difference in height. So specific gravity S1 is equals to 1.5, so rho 1 is equals to 1500 kg per meter square. Specific gravity at point B S2 is equals to 0.9, so rho 2 is equals to 900 kg per meter cube. Pressure at point A is nothing but 1 kg per centimeter square. So it is nothing but 1 into 10 to power 4 kg per meter square, and we know that kilogram force is nothing but 9.81 Newton. Therefore, it is nothing but 10 to power 4 into 9.81. Similarly, PB is equals to 1.8 into 9.81 into 10 to power 4, and density of mercury is nothing but 13.6 into 10 to power 3 kg per meter square. So taking Xs as an atom length, so PA, PB has been given, rho A, rho 1, rho 2 has been given, mercurium densities also has been given. So for left limb purpose, the equation is first for H purpose, rho purpose, density of mercury rho m into G into H plus rho 1 G into this total gap, So it is nothing but 3 plus 2 meter and plus pressure at point A. Similarly, for right hand limb purpose, it is nothing but rho 2 G into this total height H. Into pressure at point B. So this total height is nothing but 2 plus H. So it is rho 2 G into 2 plus H plus PB. So above x-axis, at the side of x side, we have written this equation as 13.6 into 10 to power 3 into 9.81 into H plus 1500 into 9.81 into 3 plus 2 5 plus PA. So this equation can be further solved. At right limb, it can be written as 900 plus 9.81 into H plus 2 plus PB. Okay, so here again we have solved this equation. Equating two equations, we wanted to calculate the value of H, and H is equals to 0.181 meter. Okay, so this is the formula or methodology to solve this equation. Okay, so here we have seen some problems. If time permits, we will take one more lecture on the same timeline, that is for solving some problems on the pressure measurement, and I'm concluding it here. Thank you very much.